second in 10 to 36 atoms. So the standard model predicted something on the order of 7.6 SNU, so neutrino unit, while was seen by Davis it was only 2.56. This means 1/3 less than expected. This is the rise of solving neutrino problem. Now, there are possible explanations about this solar neutrino puzzle. The first one is to suppose that the standard model is not correct. For sure, the first thing we can say. But there are other kinds to study or to prove the solar standard model. One of them is the helioseismology. That is the same kind of seismology that we apply here on Earth. It studied the interior of the Sun by looking at its vibration modes, and it seems that helioseismology say that the solar standard model is correct. In any case, it can't account for the detection that is 3 times lower than predicted. So, the solution of the solar neutrino problem can't reside in a not correction of the solar standard model itself. Maybe a mistake is wrong. I mean, the detector count less neutrino than predicted. And for this reason, other detectors were built at the beginning of 1980s in order to detect how many neutrinos actually we are waiting for. Or maybe another explanation is that something happened to the neutrino from the center of the Sun to the Earth. This is the hypothesis we can test. So, other experiments were built in order to study. The second one, after a mistake, was the Kamiokande detector in Japan. They started with a Kamiokande, and then it was replaced by another pure water, viewed by 1000 PMTs, a photomultiplier that converts light into electrical signal. And the reaction is this one, is an elastic scattering. This means that a neutrino of each type can be electron, neutrino, mu neutrino, time neutrino, can scatter electron, and you detect the light produced by the electron that is scattered by the neutrino. Okay? And you detect light from the Cherenkov emission. So in this, you can make a spectroscopy. Not only you can make a spectroscopy, for example, is the direction of the impinging neutrino. So the electron has the same direction, and you can look, you can point directly to the center of the Sun. You see, for example, here is the cosinus. The big amount of the event took at 1. This is the interior of the Sun. The first picture that gives directly what you see inside the Sun by neutrino. It's the neutrinography. It's some sort of when you make, for example, you can see bone inside the body with X-ray. This is the same thing. Okay. This is the first result, but on the other side, they found, both experiments found that the neutrino detected was 2 times lower than prediction. This means that for the second time, people saw less neutrino than predicted. The fact that it's 2 times and not 1/3, we will speak later because of this. In any case, we have built other 2 detectors, always employing radiochemical issue, I mean neutrino on a nucleus, as in the case of a mistake, but in this case was employed gallium-71. The fact that we wanted to this nucleus and not the chlorine-37 is because the threshold is very low. So the threshold is here, and thanks to this reaction, you can see this neutrino from here to 15 electron volt. Like in the case of gallium, in the case of chlorine, you start from here. You see only neutrino that I'm saying that you are not able to see the p neutrino. And the p neutrino is less modeling dependent than neutrino from boron state and the higher. So there were two experiments. The first one built in Gran Sasso, in Italy, near Roma, Callex, employing 30 tons of natural gallium, and the other one was here in Russia, in the underground laboratory of Sun, employing 50 tons of metallic gallium. Both experiments saw less than neutrino. In this case, they saw 60%, about 60%. These experiments were also tested with an artificial neutrino source made with chromo 51 that give a monochromatic line, a monochromatic neutrino, and you know very well how many neutrinos your source give, and you can say what is the efficiency of the detector. So you are confident that the detector is able to see almost 100% of the neutrino spectrum. You know, you can compare what is the efficiency. Do you understand what I mean? Okay, you can, in the case of stake, okay, you expect from a model how many neutrinos you have to count, but you don't know how many neutrinos really you have in the sun. But with an artificial source, you can tune how many neutrinos you want and check how many neutrinos you detect, so you can account for. Okay? So, in this case, also in this case, you count less neutrino, and now at this point we are sure that we see less neutrino than the detector. We know that the solar standard model is correct by this technology. If I come back to the three possibilities I gave at the beginning, this is correct. All detectors say the same thing, that there is less neutrino than predicted. The only possibility is that something happened to the neutrino from its creation at the very center of the sun to the detector. So this is the three experiments: chlorine, gallium and sage, the expected number and the number founded, always less, 1/3, 1/2, 60% almost. Okay. So I say that the third possibility is that something happened to neutrino. We know that in the standard model, neutrino are massless particles. But if we suppose that a neutrino have mass, or here is the case of we have only two neutrinos, mu and the electron neutrino. So it's not important that both have mass. It's enough that one of them has a mass. The difference of mass is different from zero. And if we suppose that the mass eigenstate are different from the flower eigenstate, I can write mu mu Newton in terms of mu1 mu. These are the mass eigenstate, which one with the mass m1 m2, and I can write in this way, and theta is the analogous of the Cabin-Bode angle in the quark center. So in this way we start from a neutrino that is a mu neutrino, and it evolves, changing its nature in another kind of neutrino. In this example is a mu neutrino that become an electron neutrino. This is not an epsilon. It's a neutrino that become again a mu neutrino. This is the phenomenon of oscillation. Okay? So this is the probability that a neutrino become a mu neutrino, and you see that in this formula you have 4 parameters, 2 depending upon the experimental parameter, that is the distance between the source and the detector, and the energy. You see that the probability depends on energy. This show why, for example, on steak, so 1/3 and garlic sensei